All right, everyone, let's get started. Hello and welcome to our session, Start Me Up using Peak NanoPlex HDC capacitors for motor start applications. My name is Jalen Lewis and I'm the events manager here at Peak, and I will be kicking us off today. I am joined today by Mike Human, Chief Analyst at Ignition Research, along with John Tomko, our Principal Product Development Leader, and then our guest presenter, Joseph Gottlieb, a startup CTO and technology specialist. Today, they will be hosting a panel discussion to dive into motor start applications. So before we get started, I have just a few housekeeping items. Questions will be answered via the Q&A chat following the session, and the webcast is being recorded and will be made available to you in the next 48 hours. This is a monthly series, so be sure to watch out for our December session, The Electricity Economy, Preparing the Grid for AI's Load Growth, where we will discuss the growing power gap and what might fill that void, along with our top 10 predictions for the next decade. Without further ado, I will now pass it off to Mike Human to get our session started today.
Thank you, Jalen. And good morning or good afternoon to everybody out there. Again, if you have questions, please put them in the chat, or not in the chat, but in the Q&A, and we'll be happy to answer them. So our first question is kind of looking at motor start and motor run capacitors. What do you guys, Joseph and John, kind of see as the biggest applications for these devices?
So for motor starters, in single phase motors, you absolutely have to have a start cap and a run cap. And the start cap is, a tricky bit that's required because it gives a little extra phase shift to kick a motor off and get it started. And they live not in the greatest environments. And if anyone's had an HVAC system, you've had a guy come out to replace yours. So that's, one of the most popular uses for these type of caps.
Yeah, just expanding a little on that. I think here we put down garbage disposal as kind of an interesting use case because I don't know if you've ever had your garbage disposal go out, but you can kind of see the interior of the design there. If the capacitor fails, it is basically impossible to reach. You're effectively having to replace your entire garbage disposal. And so really like where you see these single phase motors is most residential systems. Almost everything in your house is powered by a single phase motor, at least in the United States, because that's what you can plug into the wall. And so, yeah, kind of just ubiquitous use in residential situations.
So would you guys say this is mostly a residential problem, or are there industrial applications as well, commercial?
Anywhere that uses, a 5 horsepower motor or less is almost always, a single phase. They don't, and which will require, again, as we'll show coming up, start cap and run cap. And those are the most sensitive components that, will go out, from pool pumps to, again, HVAC, disposals, pretty much anything that spins that's less than 5 horse, very high probability that it's single phase.
So that could be washer and dryer, for instance. Those probably also.
Absolutely.
Okay, cool. Very cool. Well, since you kind of queued us up there, Joseph, let's jump to the next slide. And I guess if you guys want to talk about, we'll start with John this time, the difference between motor start versus motor run capacitors, that'd be great.
Yeah, I mean, the names kind of give it away a little bit. The motor start capacitor is used when the motor starts, and when the motor's kind of in its steady state and running, you're relying on a motor run capacitor. I don't know who's on the call, if we have any electrical engineers, but simple circuit diagram on the top left there kind of highlights this. The start capacitor is essentially just supplying a little bit of phase lag so that you can actually rotate the magnetic field inside the windings to actually get the motor spinning. If you don't have this, the north and south pole in your magnet just kind of stays stuck. And so fundamentally, without a rotating magnetic field, your motor's never going to move. And so kind of the summary here is that the start capacitor is really what gets your motor spinning up. One of the key things here is once it hits about 75% of its rated speed, you'll see that centrifugal switch there kicks off and pulls the capacitor out of the circuit. And so from kind of a design perspective between these two capacitors, the motor start is really just this very short duration, get the motor spinning up to speed, and then it's pulled out of the circuit. And so you're kind of just seeing this quick burst of energy. In contrast, the motor run capacitor, it is there all the time. It is the entire time the motor is running, this capacitor is introduced to the system. Yeah.
Yeah, just to expand on that, the motor run, again, for those electrical engineers out there, it gives you a better kind of, power factor between your voltage and your current, and gives you better efficiency. Which is why they put the motor run in there. And the motor start is kind of taking the brunt force, as John mentioned, when the thing first comes on, when you first energize it, that cap is what gets it kicked off, gets it rotating, gets it up to speed, and then it's, out of the circuit. So it's definitely taking, a pretty large amount of abuse, especially if you think about garbage disposals, turning them on and off all the time, HVAC systems on and off all the time. So there's a lot of abuse that gets. And again, they're located in poor positions to be replaced. They're in, hot areas, which is not great. And we'll get into those, those details coming up here soon.
So essentially, when a motor start capacitor fails, it sounds likely that you're gonna just replace the whole motor.
It depends. So, slightly like HVAC systems, they design it, you can see the ears on the bottom. You can get to those, that bottom picture, it's got those kind of hoop ear kind of parts. You can take those off and get to them. But that whole motor is usually up inside of another assembly. Like when you look at your HVAC unit, it's a nice clean box. Well, you got to take the cover off that box. Then you got to get to the cover where the caps are. Now they do put them in replaceable places because they know they're going to blow up. They know they're going to have problems with them. But if you bury a motor somewhere, if you've got a water pump that you got to put down in the ground, or you got to put somewhere else, man, it's a nightmare. You got to pull the whole motor to get to it.
Sounds like fun. I was also looking at the difference in the material used for the capacitors. So electrolytics on the motor start and oil-filled polypropylene on the motor run ones. Is that because of the difference in current they take, or just the higher capacitance? What's your guys' view on that?
A big part's lifetime as well. I mean, it is what you said. You have different capacitance needs for start versus run. There's slightly different operating voltages. It's pretty rare to see an electrolytic at 400 volts AC, for example. That's kind of an extreme case for electrolytics. But the big thing is that, again, the motor start, you're only using it for, depending on the application, maybe 2 seconds a day. In the case of HVAC, it's 2 seconds. It's in use for 15 times a day, maybe, but fairly low relative to running, where the HVAC's under continuous operation. And so you typically see film capacitors for motor run, because they can take kind of that sustained continuous current over tens of years. Whereas as an electrolytic, you're lucky if you get 10 years with that low duty cycle.
Very cool. Speaking of that, what are some of the challenges that you guys see with the current materials that are used? And Joseph, we'll go ahead and start with you on this one.
Yeah, I mean, you can see that upper left picture, and I've done this multiple times. I don't know if any of you have replaced your own starter cap, because, if you do it yourself, it's like 30, 40 bucks for a cap. You have a guy come out, it's, 300 bucks. But what you can see is when it fails, you usually have a pretty catastrophic failure, and it will burn the wires in there. It's all UL rated stuff, so it's not going to set the side of your house on fire, burn the unit down. But man, you get a lot of smoke. You get a lot of charred wiring inside. And electrolytics don't fail. They fail spectacularly. They don't fail mildly and just kind of go into the night.
And spectacularly in a bad
Right.
way, I take it.
Yeah. There's other things too. I mean, not only do you have the spectacular failure, but again, we're using electrolytics for the start. And so, depending on, again, that duty cycle conversation, electrolytics have terribly high internal resistances, and so the more current you're putting through them, the more loss you have, the more energy consumption the system has. And so, you're looking at kind of the directional chains where we're trying to conserve as much energy on every application as we can. You can envision electrolytics really aren't fitting into that equation very nicely. And so, again, going back to in the motor run case, this is where you see a lot of film capacitors. one of the main advantages is that they have a low internal resistance. So you're just not losing as much electricity in using your device over time. One of the main reasons you don't see film capacitors in the start case is actually the size limitation. Again, you have these different needs of capacitances. If we took every electrolytic capacitor and switched it with standard polypropylene film capacitors, you'd see every system size have to increase correspondingly. And so, one of the limitations on even starting the conversation around changing out of electrolytics is what's the better alternative? And you have to have these engineering trade-offs as you introduce them. And so that's, again, kind of just a fundamental limitation.
So assuming this can here in the left picture is the capacitor, the electrolytic, if you were to replace on the film one, you'd be looking at something significantly larger, I would assume, like 3x, 4x, 5x in size or something.
Yeah, absolutely. Absolutely. And you can see that's already a fairly large capacitor relative to the size of your HVAC. That's not a tiny little resistor sized element. So yeah.
The one thing that really caught my attention in both these comparisons is the thermal sensitivity, right? You have on the electrolytics, the capacitors drying out in high temperature environments. And even with the BOPP film ones, the run capacitors, you've got a limited thermal sensitivity. And interestingly, for something like air conditioning, that would seem to be an Achilles heel in the sense that usually you're using your air conditioning when it's really hot outside. So, is that a big issue that you guys see?
Yeah, I mean, in this particular case, what you'll see is that electrolytic is kind of away from and shielded from the internal, motor that's actually running the main blower part, because they try to get it away from the heat, as best they can. In other motor designs, they have to have, kind of some airflow through those little chambers that the electrolytics hold to. And so a lot of times, you'll be paying a very high premium for, hermetically sealed motors that have the cap hermetically sealed, again, because it becomes a major problem. You're really sealing in that heat, and these things they don't do well. They'll dry out much quicker, and you'll be replacing, the cap or the whole motor, much more often.
All right, let's go to the next slide here. So one of the things that we're talking about in this webinar is Peak Nano's NanoPlex HDC film. John, you want to talk a little bit about that and kind of what that means and why it's important in this particular use case?
Yeah, I actually didn't realize this was the next slide, so this works out very conveniently. I just explained how, we can't switch electrolytics to film capacitors because you have this engineering constraint of size. I mean, that really is a core critical element. You have much larger capacitances. It's already a huge element. We're not going to make it 4 times bigger for film. So standard film capacitors just simply won't work. And there's really nothing alternative on the market from polypropylene that approaches the same capacitance density that you would get out of an electrolytic. And so one thing Peak Nano's developed is this HDC film alternative. And so it's a high energy densities film that can directly replace polypropylene, but get you to these much smaller capacitor sizes for the same element. And so there's a nice bullet point there. If you took a polypropylene capacitor and switched it for HDC, you typically see 2 to 4x reduction in size. So this goes back that now you're actually in the ballpark of where the electrolytic is fitting. And so it's kind of this nice plug and play replacement. One of the other things is it was really tailor designed for pulse power applications. So we go back to this idea of what's the duty cycle? What's the lifetime we need out of it? And HDC really fits that kind of very specific application point where it can handle these strong impulse currents. And it also has the ability to kind of tolerate slightly longer duty cycles than you would even see in electrolytic. You're hitting equivalent or lower internal resistances. I think the one caveat on this that I think we always have to mention is cost. I'm definitely not going to lie and say that HDC is cheaper than electrolytic. You can buy electrolytics extremely cheaply. The trade-off is exactly what Joseph said. Every time your HVAC fails and you have to pull out a service tech to do it, you're looking at minimum $40, usually hundreds of dollars per capacitor. If instead you could just have a single long lifetime element, you would actually find even if it was double the cost, let's say, it's not, but let's pretend, if the capacitor costs double, if it's never replaced, actually spent less money over the lifetime of the device. And so again, this is kind of one of those cost engineering comparisons that you always have to make. But yeah, HDC is kind of this nice plug and play replacement for electrolytics, but gives you the properties of that film capacitor that really give you much longer lifetimes and better reliability.
And I see that on the availability and supply chain, primarily Asia imports, primarily from China versus the US based. So I guess if you're trying to increase the total US value in your product, that's certainly a good sign as well.
Yeah, and I think there's also the aspect of not just, everybody likes US manufacturing when we can get it. But what you typically see with a lot of the electrolytics you import from China is you actually just don't get good reliability metrics. You can buy 5 of the same capacitor and 4 work great and 1 doesn't, and you don't know until your HVAC fails a year later. Having that kind of internal US supply chain, you typically associate that with a lot more engineering rigor and certainty around it. And so having that domestic supply also kind of gives at least the conversation where you can get those reliability metrics, that get that data sheet to you as needed.
So kind of in a sense, back to your point of saying, hey, you might pay more upfront, but in the long-term life cycle, you're a lot better off. And
Yeah.
who likes their air conditioning going out in the middle of a heat wave, or their washer breaking when it's full of wet clothing? Neither are good situations.
Well, and in some cases, you might not, necessarily pay more. Again, with today's, tariff magic going on, bringing these parts in is costing more and more. And then the US with BOPP requirements, Build America, Buy American, there's definitely a large push for any kind of critical infrastructure pieces, which do have a lot of single phase motors in them that do have, these requirements. Anything on power infrastructure, which I'd like to make a comment about. Again, stable with strong ripple currents and the higher temp capabilities and the pulse capabilities of the HDC. One of the great things is that a lot of times when the grid goes down and then comes back, that's when your equipment really takes a hit. Because not only is the motor having to start again because power shut off, power's coming back on, but the quality of power is usually really terrible. And the way that it comes back on is very harsh with high harmonics, lots of peaks. There is a lot of damage that occurs to those caps in those cases. So having something like an HDC film cap that can handle those type of situations is far superior. And again, just leads to that much longer lifetime. If you don't have to replace these things, your long-term costs are going to definitely go down.
That's a great point. That's a really good point. I understand that one. I'm living in Southern California, power going out. I know, Joseph, you understand that one too. For wildfires or other things, it is when your stuff breaks and the power comes back on a lot of times. So
Yeah, brownouts are terrible. It's why you got to put a UPS and surge protector on your computer, right? But your computer power supply full of electrolytics, and it takes the brunt, and with surge protection. But again, it takes that brunt of it, and those electrolytics don't like it. So if your surge protection isn't good, those electrolytics take the hit, and then their life is short.
we talked a little earlier about failure mechanisms of electrolytic capacitors. John, what is the failure mechanism for an HDC capacitor used in an electrolytic application?
It's a gradual failure. You get that benefit you see with film capacitors as a whole. You're going to see this very slow decay of capacitance. I will tell you, this is going to slow down your motor over time as it starts to fail, but you won't wake up one morning and your washer and dryer aren't turning on while you have wet clothes in there. Instead, what you'll see is this slower and slower startup actually take on. You'll see this with every film capacitor. And so it's kind of just the fundamental difference between film versus electrolytics. But no more spectacular explosions, unfortunately, I guess, for some people.
And it's detectable.
Yeah.
So that for the Maytag repairman, but not bad for you as a consumer.
Right. Well, the units can now self-diagnose themselves as they see their start, as they watch the motor spin up to speed. They can see that time getting longer. They can make a notification that says, hey, my caps are starting to, something's going wrong here. Either, the motor's got a problem or the cap's got a problem.
Nice, very nice. So there are other materials that obviously out there. We talked a little bit about biaxially oriented polypropylene, also known as BOPP. Pen is another one that's out there that's supposed to have good characteristics. Do you want to talk to this one, John and Joseph, and kind of say what you think the advantages are of Nanoplex versus pen or BOPP?
Yeah, I'll take a start at this and then Joseph can add in. I'll start with pen in the middle here. I made the comparison of electrolytics to polypropylene and how HDC really fills that niche by being able to hit the electrolytic capacitance density you want, so smaller capacitors. Pen is kind of approaching that. Pen is more in that direction than polypropylene. If you asked me years ago, what I would have suggested to replace if you want a film capacitor would have been pen. The fundamental limitation is it's not being manufactured anymore. I can go through the spec sheet here if we want, but I don't think it's informative just from the pure perspective of it doesn't exist. With that being said, without going into every nitty-gritty detail, what I'll tell you is Peak Nano has spent actually a good amount of time developing a second film series to kind of act as a plug-and-play replacement for pen or even polypropylene in certain application spaces. And so, trying to fill that supply chain gap that exists that pen kind of left behind, LDF, when compared to polypropylene, is giving you much longer lifetimes. It can handle these high currents. So going back to power grid starts up, you have this terrible case of power coming in. LDF is going to be a lot more tolerant to that than standard polypropylene would be. The general lifetime is really enabled by the fact that it's actually a high temperature material. So we go back to kind of, we can put in these engineering constraints where we basically have to physically remove the cap from the high temperature regions of our motor. In contrast with LDF, you don't have to go through these thermal design challenges. It can simply tolerate the heat. I could put the cap up to 135, which is much higher than most HVACs are going to run at, even on the hot side. I don't have to do any forced cooling. And so from, again, this engineering design perspective, LDF, yeah, you'll have a bigger size capacitor, but I can put it anywhere I want. And so in certain cases, I can actually kind of tolerate that larger design because I'm not limited by the needs for cooling.
So from a system design, it sounds like it's, has a lot of advantages and yet makes your system design significantly simpler.
That's really what it is. I would say LDF is fairly comparable to polypropylene. Very similar cost. You'll see typically the same resistances and things like that. The big thing is it tolerates high temperature and has long lifetime. And so, yeah, if I'm a systems engineer, I would much prefer to work with LDF over polypropylene simply because of that reason.
That's a big one.
Yeah, the high temp is becoming much more critical in power electronics in general because you don't want to make these massive size systems. You want to build, much more compact. You want to make them much more dense. So you build your little bank of electrolytics, but man, you got to leave some space in there for your air gaps in there. But with these guys, you don't. So you've got, the high temp capability, you have the high voltage capability, which opens up a whole nother arena of applications. You don't have the venting, kind of issues like electrolytics, so you can go to high altitude. It just has all these, fantastic specifications, and at a cost that's comparable. It's it's very interesting. It's very, very interesting. I think it's going to expand a lot of design capabilities, and those are the big takeaways.
Excellent. So I guess before we jump into the Q&A side of things, let's say somebody's interested in getting these. John, how do they go about doing that? They want to get some samples, that sort of thing.
Feel free to call me anytime if you want. Phone line's always open, some emails here and there. I would say Peak Nano's website's usually the good place to start. We have a nice way of kind of easy access to our marketing and sales teams. But I think for a lot of what I'll say general cap manufacturers, there is a qualification process associated with kind of any new film. And so Peak's really set up a really nice pipeline where we've kind of been working with a large array of customers and can get them samples kind of as quickly as possible. And so, we're recognizing most people don't need these very extremely large inventory rolls right now. And so we can usually get film out the door pretty quickly. So short answer to your question is call me anytime or go to Peak Nano's website and drop an inquiry there.
Sounds excellent. Jalen, let me turn it over to you for the Q&A part of the program here.
All right. Thank you all. As we are opening up our Q&A portion, I do want to bring your attention to the 2 links that are available in the chat. So if you're interested in learning more about what they were talking about with HDC and what Nanoplex is, both of these resources will be very beneficial for you. And so with that being said, let's move into some of our questions. I believe that you targeted this one a little bit earlier, but what is Nanoplex's failure mechanism versus electrolytic caps?
Yeah, I think I hit it earlier, but just to repeat, electrolytic caps they basically explode. There's no way around it. Your motor's running, and then the next day it's smoking and it doesn't turn on anymore. What you would instead see with an HDC type capacitor, or really any film capacitor, is a more gradual failure mechanism. So your motor's getting slower to start up, and things like that. So you kind of get this early warning mechanism instead, like Joseph mentioned.
There's
Yeah.
there's also some self-healing capability in certain cases, right?
Yeah, that's a great point. Yeah, so LDF in particular is really designed with that self-healing in mind. So when you compare it to polypropylene, which is known for how good it self-heals, LDF is certainly comparable to that. And so what this means is you actually aren't really seeing extreme reductions in capacitance. It can really tolerate kind of these short bursts of failures over time. And that's why you get such a long lifetime out of it. It's a good point.
The next question comes from Maria. What is the ratio in cost between LDF and BOPP?
To be honest, I wish I could give the exact number, and my memory is just not good enough to tell you the price that we sell LDF for versus BOPP. What I can tell you is they're really close. It's close to 1 as a comparison. I can give you a more concrete answer, Maria, or anyone that's interested. I literally just need to pull up our table of prices, and I don't have that on hand, and I apologize.
And a follow-up question to that. Oh, I apologize, Joseph.
No worries. I was just going to say, I think one of the reasons as well, the cost parity is that material is a direct replacement for film materials and existing cap packaging equipment. So the cap manufacturers don't have to do a giant line change or technology change to put this into their film caps. It's an almost direct replacement in terms of take this film out and put the LDF film in.
It's a big one.
Next question is, what are the main improvements on LDF compared to previous Peak 3125 and 4125?
I wouldn't really call it improvements. I would call it differences. And the reason for that is they're different product lines fundamentally. So HDC is high dielectric constant is kind of the abbreviation there. LDF is low dissipation factor. And so the truth is you're kind of making a trade-off here. Do you want a high dielectric constant or do you want a low dissipation factor? Now, of course, even with a high dielectric constant, we're still working to minimize that dissipation as much as possible. So trying to minimize the internal resistance. You're just never going to get a dielectric constant of 4 and the dissipation factor of polypropylene. I just think it like breaks physics at some point. And so that's really the comparison between LDF and HDC. LDF really is a true plug and play high temperature replacement for BOPP. You get the same very low dissipation factor and almost exactly the same dielectric constant. HDC is really designed with that intent of just pushing the dielectric constant as high as you possibly can for energy storage and pulse power needs, where you can tolerate slightly higher dissipation factors. So I hope that answers the question, but I would call them differences, not really improvements. Yeah.
Right. Our next question is, how mature is Peak's Nanoplex versus other comparable materials?
People are using it. I'll put it that way. People are putting them in capacitors and making capacitors out of it. I would say that the one, active limitation we have on Peak NanoPlex isn't in the film itself, it's on the manufacturing side of things. We simply have been scaling up through this kind of R&D process into pilot scale, and now we're just hitting the point where we're moving into manufacturing. And so Peak is targeting mass manufacturing in kind of late 2026. And so from a technological maturity perspective, it's there. It's just getting it to the point where we're able to put out these large inventory orders to kind of supply the much larger capacitor needs that people are looking for.
All right. And then John, kind of going back here for a second, Maria had an edit to her question, but she said her question was actually related to HDC compared to 3125 and then 4125 rather than LDF in terms of improvement.
So we don't have an HDF. So Peak Nano has HDC, high dielectric constant, and LDF, low dissipation factor. And then within HDC, there's two main product lines we typically offer, which is HDC 3125 and HDC 4125. And so the differences between 3125 and 4125, 4125 has a higher dielectric constant, but also slightly higher dissipation factor. 3125 is a little lower on both. And so again, kind of just engineering trade-offs. I hope that answered your question, Maria. Nope, not a problem at all. Yeah, we use too many acronyms. I don't disagree. I totally understand.
True of our industry in general.
Yes, yeah.
All right. And I am seeing a couple different questions coming through about getting samples for the nanoplex-based capacitors. Just to sum up what John said earlier, the Peak Nano website is a great source for that. And as well, in the follow-up that you will email that you'll receive from us after this webinar, it will have direct links where you can fill out the forms in order to get all of these samples. So it should be something very easy for everyone to get access to. And
We'll
with
include
that,
John's phone number as well, I guess.
yes, yes, I can add in all of those resources as well. And with that, that's going to conclude our webinar today. That's going to conclude the Start Me Up using Peak NanoPlex HDC capacitors for our motor start applications. So if you have any questions that were not answered, we will reach out to you directly with those answers. And thank you to all of our viewers again for joining us today. Thank you, Mike, for leading our discussion, and then Joseph for joining us on today as a guest presenter, and then John, of course, for answering all of those technical questions for us. So if you're interested in joining us again, please pay attention to your inbox where you are going to receive the slides from today, collateral around the discussion, and then more information about our next webinar. So if you have any topics that you would like to see, or if you would like to join like Joseph did today and be a guest panelist, please reach out to whatsnext@peaknano.com. And so thank you again for attending, and please stay connected through the following platforms.
Thank you, everybody.
Thanks all.